Hello, everyone. I hope everyone is hearing me. So, welcome to EPMA's webinar series number 3, which is on hipping. Today we will have a nice discussion. Actually, we will have some kind of good information from Nerya Ordas of SEIT, who is a senior researcher. She will be rather giving the theoretical background of hipping to the audience. And then afterwards, we will have Jim Shipley from Quintus speaking on the practical applications of hipping. So if Nerya and Jim, are you online? Can you say hello to our guests?
Hello, good morning, everybody.
Yes.
Yeah, okay.
Good morning.
Yes, actually, before starting the webinar, we came together, but I want you to show yourself to our audience so that they feel more comfortable, and that will be a warm welcome. So thank you for doing that. As I said, we will today have two nice presentations, one from Nerya and one from Jim. And after that, we will have a good Q&A sessions. Even I have some questions to both of you that I would like to learn about hipping, because it's a very special process with good enough technical details. So therefore, I don't want to spend too much time and start. And as you may know, typical to all EPMA events, I will start with a short presentation about EPMA and its activities. I'm sure most of you even memorized these slides, but at least for the audience who follow an EPMA event for the first time, or for the people who wants to learn other activities of EPMA, it can be a good chance. So let me first screen my slides regarding the EPMA activities. So yeah. Okay. Yes, before starting my presentation, I would like to make a few announcements in general necessary for these type of events. Please prefer to use your headsets rather than the internal microphones of your laptops. That's much better for the sound quality. And while you're not talking or presenting, please turn off your microphones and cameras. In case you would like to ask a question or say something, you can raise your hand, and you can also use the chat screen to ask your questions. By the way, we also have Bruno Vicenzi and Andrew Cormack from the team of EPMA, who will be assisting through the chat screen for your questions or any other issues. Okay, so let's go on. As I said, today's webinar is the third webinar on EPMA series of free webinars for public. Here the goal is to raise awareness for everyone related with powder metallurgy. The agenda is, as you can see, I make a short presentation on EPMA and its activities in hot isostatic pressing. And then we will have Nerya giving us the theoretical background of hipping with the fundamentals. And then we will have the presentation of Jim. He will talk on the applications of HIP with really nice case studies. And then we will have quite a long Q&A session. I would prefer to have long Q&A sessions in such webinars, because really nice questions are arising, and interactivity is really important in webinars. Otherwise, it's so dull and boring. I know this from my own experience while following some webinars as an audience. So please do not hesitate to ask questions. Feel free You can ask your questions by raising hands, and when you want to ask your question, you can unmute yourself, put on your question. We will welcome that. So, shortly, who is EPMA? EPMA is the European Powder Metallurgy Association. It's a non-profit association formed in Brussels in 1989. We have three key missions. The first one is to promote and develop the powder metallurgy in Europe. The second one is to represent the powder metallurgy industry, either in Europe or on the international base. And also the last and the most important one for me, I think, is to develop the future of powder metallurgy. Actually, there's a good definition of EPMA. EPMA is what its members want it to be. I like this definition really too much. Okay, when you go back to the historical background of powder metallurgy covered by EPMA, it all starts with Present Sinter in 1989, where the ferrous materials and then hard materials and other alloys represent here the root of powder metallurgy. And then hard materials sectoral group is formed in 1999, followed by MEM group in 2001, and then currently we have 6 sectoral groups within EPMA, the last one being functional materials set up in 2018. So all these new materials, new processes, new needs create new sectors. Therefore, I think this will go on. We will have some more sectors added to the chain of EPMA in future. For the sectoral groups, as I mentioned, we have 6 sectoral groups. Each one has quite good enough activities. For example, they organize seminars, they have their own meetings, and we also prepare surveys either for statistics or for benchmarking or even for trend surveys. And also all these sectoral groups have the publications such as the brochures or the booklets. As you can see, we have currently the AM, the HIP, the MEM, and the Present Sinter booklets. These are available for free download on EPMA website. And currently we are working on preparing the functional materials and the hard materials booklets. We hope to get them ready in 2021, so that for each sectoral group we have the booklets. These are kind of manuals or simple basics of all these technologies. Especially the AM case is a kind of handbook for everyone in the additive manufacturing business, and we even prepared the 3rd edition due to final developments in the industry, so it's improving and progressing step by step. So regarding the working groups, we have 2 main working groups in EPMA. One is the EHQS, Environment, Health and Quality Safety Working Group, and then we have the European Powder Metallurgy Institute. So if I would prefer to explain what they are briefly, let's start with EHQS. EHQS Working Group is, as I said, focusing on 3 main subgroups. This is the standardization, such as ISO, DIN, or ASTM from the United States. LCA, the life cycle analysis and the environmental impacts, followed by Bruno, my colleague. And then the chemical management, that is the regulations and legislative issues such as REACH CLP. For ISO activities, I can say that EPMA is the liaison office for TC 119. This is the Technical Committee of Powder Metallurgy, and also the liaison office for 261. This is the Technical Committee of Additive Manufacturing. You can follow all our activities either through EPMA website or the newsletter that I will be explaining in the next slide. Regarding EPMI, the EPMI Institute of Powder Metallurgy focuses on development of projects between partners, transferring students and staff from the education to the industry side, and support EPMA in these activities of education and research. So it is a very strong team of academicians who are, let's say, the main actors of powder metallurgy, thanks to their good effort to support us within the umbrella of EPMA. So as I said, in the EHQS working group, we have a newsletter. This is once in every 2 months prepared and includes all the news of chemical management, LCA, and standardization. On the other side, the EHQS working group follows other type of business-related information, such as the Brexit case, you know, and also coordination of EU-funded or collaborative type projects related with environment, health, quality, and safety. So regarding the EuroHIP sectoral group, I would like to mention some words. The EuroHIP sectoral group of hot isostatic pressing is launched in 2009. It is open to all companies and organizations who are in the supply chain or any place of EuroHIP and who want to be a member of EPMA. Every year, the EuroHIP sectoral group organizes a seminar. The last one we had in March 2020 in Oslo, Norway. This was just before the pandemic case, so we were not really sure of how to handle it, but we rather had a hybrid event with success thanks to our hosts in Oslo. And this year, probably we will either have a hybrid event or maybe an online event, depending on what will be the status during that time. Regarding the publications, as I mentioned before, you can download freely the hot isostatic pressing technology booklet of EPMA. This is a very good source where you can learn a lot more about hot isostatic pressing. As the EuroHIP sectoral group, we collect regular information to prepare statistics. So this is also another important activity of EuroHIP. We collect the information regarding the production, the sales, or any other business-related issues, and then we distribute the results to the members of EPMA and to the participants of survey. Here, I would like to mention an important thing. If you want to get the results of such surveys, please participate in these surveys. Usually what we encounter is that companies do not want to share information, but they want to get the results. Unfortunately, this is not possible. If you want to get some good information, please share your own data with us and be sure that if necessary, EPMA is ready to supply a secrecy agreement. We really take care of being anonymous for these surveys because we know that sometimes we really get very sensitive company data that we should not share with any other person. So, as I said, if you want to get the results of EPMA statistics on HIPing, please, if you are not a member, please join our surveys. And then, as I said, if you need, we can supply with certain secrecy agreements to guarantee that your data will not be shared by any other third party. So I would like to say some words about EPMA Club projects. This is the projects, collaborative projects between the members of EPMA with budgets of maximum up to 100,000 euros. Up to now, EPMA has completed 28 projects and raised funding of more than 1 million euros. Currently, we have 6 projects running, and in 2021, we will be starting 3 new projects. So let me explain a little bit how it works. Here, the project ideas from universities or RD centers are sent to us. And with the project proposals, we announce it to our members and call for invitation to join. And if the industry partners who want to participate in this project, we prepare a certain agreement and we share the budget between the industrial partners. And then, of course, the coordination is done by EPMA. What I can say here is that usually companies who want to make an RD work with a less budget and less work, this is a good place to do it, where they can share the load, but then of course in return they share the results. The results can be either publicly announced or not publicly announced, depending on the consortium agreement. Sometimes the industrial partners only want to share the outcomes of the project among themselves, but not public. So it is something that is discussed in each different project case. And also regarding the EU funding projects, EPMA participates in different projects, and currently we are having almost finalizing the Supreme project, and we are running the SAM project, which is the kind of education and training development Erasmus type of project. So we will have some nice webinars and activities within the project of SAM as EPMA. You can follow these from our website or LinkedIn pages. So there will be some nice webinars on additive manufacturing training and finding some job opportunities. That's the goal of the project, so develop a certain common platform for the additive manufacturing business. Please follow these activities from our website and LinkedIn. So I would like to speak also about our EuroPM Congress. This is a very important topic. Unfortunately, due to the COVID case, this year it will be held online. It will be a virtual Congress. There will be more than 120 presentations. That's a really strong Congress. So it will be a really compact program within 3 days. So you can join the event through the event website of EuroPM 2020. All details are given there. We don't have too much time to register for the event, so on the last days it's usually very difficult to register. So I would advise you to register as soon as possible and do not wait until the last day. There will be presentations all about these topics that are on the screen. That is Present Center, AM, Environment, Sustainability, FM, Hard Materials, Hipping, MIM, and Materials, Processes for Specific Applications. We will have a really international speaker portfolio from US to China to India, but of course mainly Europe. So you can also see the program now. It's available on the event website. All speakers and sessions are announced, but don't forget that these might be open to some slight changes. So please follow the program regularly on the event website. That's all I would like to say about EPMA and its activities on hot isostatic pressing. Thank you for listening. Now I would like to give the word to Nerea. So Nerea, if you are there, yeah. Oh yes, you're here. Yes. Hello once again. Now I think it's now your turn to speak about hipping. So I give the word to you. So good luck.
Okay, I'll try to share my screen and open the presentation. Okay, can you see the presentation?
Yes.
Okay, thank you. So again, good morning, especially to all of you that joined later. Well, in this presentation, as Kenan introduced, I will try to give you a brief introduction to the fundamentals of powder consolidation by hot isostatic pressing. And the core of this presentation is basically a brief description of the densification mechanisms involved in the consolidation by heat. And I also will give you a short introduction of the role of modeling activities to predict and control the shape they change in complex components. Heat can be basically described as a forming and densification process that combines the simultaneous application of high pressure and high pressure and high temperature. And thanks to the application to the use of a heated gas to apply this pressure, it's applied uniformly in all directions, so the linear shrinkage is the same regardless of the direction. Well, although Jim will explain later in detail the main applications of hot isostatic press, I will briefly tell you that the heat can be used for three main applications. First is the densification, removal of pores that can remain as a residual defect in products produced by other technologies like casting, additive manufacturing, MIM, metal injection molding, or even sintering. It can be also used to join similar or dissimilar materials under solid state, in those cases where it's not possible to melt the material and use welding or brazing. And it also allows to consolidate powder that can be metallic or even ceramic, provided this powder is contained in a capsule, in a container. And this last case is the topic of this presentation. Okay, HIP, as you will see, is a very flexible process that can operate at temperatures, at a broad range of temperatures and pressures. Temperatures can reach, depending on the heating element of the heat press we are using, can reach 2000 degrees, and the pressures can be as high as 200 megapascals. This is not usually the case of the industrial presses, but this is something that can be achieved. It allows processing a wide range of materials, as I've said, and also samples, components of very different sizes, from few grams to several tons, with the only limitation of the chamber of the heat press we are using. As you can see on the screen, there are HIP samples very small, with a diameter of a few millimeters, and we have one very big hip press in Japan with a diameter of more than 2 meters and a height of 4 meters. Here you can see some of the main advantages of the hot isostatic press applied to the consolidation of powders. Since it's a process that takes place in solid state below the melting point of the metal or the solidus temperature of alloy, very fine, homogeneous, and isotropic microstructures can be obtained. Also, fully dense materials can be achieved with no segregations nor inclusions, typical, for example, from encastings. On the right side of the slide, you can see an example. I've shown here a microstructure, a typical microstructure of a superduplex stainless steel for oil and gas applications. You see that after forging, this microstructure is quite elongated, but after heaping, the microstructure we obtain with the powder metallurgical grade equivalent to that forged material, well, you can see it's very fine and homogeneous. One of the consequences of this high quality of the microstructure is that the properties in general, all the properties of the materials are improved. In this case, the mechanical strength is higher, it's clearly higher, and also the ductility. But we do not only improve the mechanical properties. We can also enhance the fatigue resistance at high temperature, also create behavior, corrosion resistance, wear resistance. And in addition, for example, in complex components where we can avoid or minimize welds, this corrosion resistance is enhanced because of the lack or the minimum amount of welds. Another advantage of this process is that offers a high flexibility in the design of the components, very complex shape, very close to the final shape and dimensions can be obtained using a wide range of alloys. Some of them cannot be processed by other conventional methods like casting. And as I said, a wide range of part sizes can be produced. Since this process is a near net shape process, it can allow minimizing machining operations to achieve final tolerances. It also allows a reduction in the consumption of raw material, and also NDT testing to detect defects is easier. Some final advantages could be a cost reduction, reduction also of the delivery time, and also of the environmental impact of this technology considered as an overall. The process to obtain components by consolidation of powders by a hot isostatic press is as follows. The process starts with the production of the powder, which is usually obtained by gas atomization. With this type of atomization, we obtain spherical powders. A capsule, in general metallic in the case of metallic powders, contains the powder and isolates it from the pressurizing media. Once this capsule is manufactured and leak tested, it's filled. In order to maximize the amount of powder filled allocated in the capsule, powders with spherical and regular particle geometry with low density of satellites. Satellites are these small particles adhered to the surface of other larger particles. So I said a low density of these satellites is desired, broad particle size distribution, and and at least bimodal particle size distributions are decided. So, as I said, once the capsule is filled, then we proceed with the evacuation and sealing to remove all the air and volatiles that could be adhered to the surface of the particles, and leave the powder and the vacuum and isolate it from the surface. Then we go with the heap process, with the heap treatment at a certain combination of parameters. And then sometimes the heap is not, the heap treatment is not enough to obtain the final material with the desired microstructure, and it's necessary to perform solution annealing or precipitation heat treatments. And the process finishes with the capsule removal by acid pickling or mechanical machining until we reach the final tolerances. In this slide, you can see a couple of examples where the change of volume is evident. So you can see with these two examples how important it is to understand all the mechanisms involved in the densification during heap, to control them and predict the distortions that will take place. Okay, densification take place basically in two stages. During the early stage, the relative density of the packed powder is relatively low, could be between 65 up to 75 degrees. And initially, the pores are interconnected, particles are spherical, remain quite separated, and the contacts between particles are very small. During this early stage, while densification evolves, the porosity is slightly reduced, and these contacts grow in area. But during the final densification stage, particles are no longer spherical, but polyhedral, and pores are spherical and are isolated. So there are three main mechanisms that describe this densification: plastic deformation, creep, and diffusion. Plastic deformation can be defined as a permanent deformation that takes place above the yield strength, or when a stress is applied above the yield strength. This is the main mechanism of densification during the early stages of heap, and takes place because of two main facts. One is the thermal softening. This means that when the material is heated, it loses their strength. You can see it clearly in this example on the right, where you can see an oxide dispersion strengthened steel produced by heaping. In this case, the mechanical strength and also the yield strength is very high at room temperature, but is reduced as we increase the temperature of the test. Another fact that is responsible of this plastic deformation is that these contacts between particles, initially very small, act as stress concentrators. And in fact, the stress on them can be several times the yield stress of the material at a certain temperature. So this is one of the requirements to have plastic deformation. The effective stress here should be higher than the plastic deformation. And you can see here one example of the heat press at the early stage. In this case, it's a stenitic stainless steel. As densification progresses, the number of particles is increased. Particles lose their sphericity. Pores, their area is reduced, and as you can see, the area between contacts, contact between particles increases. This means that the effective pressure acting on these contacts is reduced, as many models have described. There can be one moment that this effective pressure is lower than the yield stress of the material. So in that point, this plastic deformation mechanism is no longer effective, and we need another mechanism to continue with the densification. So we have the power lag creep. This is the main mechanism of densification during heap. It's responsible of the major fraction of densification, and can be briefly defined as a slow and continuous deformation in time. This means that deformation, permanent deformation, depends on time. Creep takes place above a certain temperature and is enhanced with increasing temperature and pressure. So well, this is why creep is more relevant at high pressure and temperature. And it is controlled by diffusion, atomic diffusion in the volume, and also movement of dislocations. And the last mechanism is diffusion. It takes place also at high temperature, and it's responsible of the final elimination of pores. And it's possible with two types of diffusion. Not every diffusion mechanism allows densification. In this case, the diffusion mechanisms that allow this densification have been represented in this figure, and are grain boundary diffusion and volume diffusion. In both cases, we have atomic diffusion from the contact area of the particles towards the pores, and in the opposite direction, we have the diffusion of vacancies from the pore to inside the particle. Okay, all these mechanisms can be described by macroscopic or microscopic models. In this case, in this table, I have included some equations that are the constitutive equations that describe these different stages and different consolidation mechanisms acting at different stages of the heap process. I won't go into detail because it can be quite boring for the first time. I will just tell that these equations can be combined to build some graphs that are very useful to define the heap parameters. These graphs are the densification maps and help to identify the mechanisms involved in the densification during heap. And also they consider some approximations, or they take into account some approximations that simplify in certain manner the process. They are very useful from the qualitative point of view for a first selection, for example, of the heap parameters. In this case, I have included the densification maps of a tool steel and the superalloy, and you can see how it's possible to find which is the main consolidation of densification mechanisms at a certain combination of pressure, temperature, and relative density in both cases. In the typical parameters of heap of these materials, you can see that plastic deformation is almost irrelevant to achieve densification in these materials, but creep is the dominant mechanisms, and diffusion allows to achieve a final total densification, the final removal of the pores. You can see that there is no only one combination of heap parameters to achieve full density. It's possible to use different temperatures of pressure. So the decision of selecting one or other will depend on the microstructure we want to obtain, or the limitations of the heap press we are working with. I have included a few examples so you can see the effect of these parameters. In this case, it's a superduplex stainless steel for oil and gas. It's being consolidated at 140 megapascals during 2 hours and different temperatures. And you can see in all of the cases The microstructure is very homogeneous and fine with the typical distribution of austenite, ferrite, and the sigma phase. You can also see that an increase of the temperature up to 1200 is responsible for a grain growth. If, for example, we have a limitation in the heap press and we cannot reach 140, it's possible to reduce the pressure and compensate this reduction with an increase in the time of the heap cycle. And in this case, we obtain a very similar microstructure in which there is no significant coarsening due to this increase in time. So we can see that some heap parameters can be equivalent. Another example, in this case, an austenitic stainless steel, consolidated also at 3 different temperatures. We could see that in the lower range of what we could consider full dense from these maps. In fact, depending on how this pressure is applied, we could find some residual porosity, very, very small, but this porosity is responsible for a weak behavior of this material. So it's necessary to achieve to increase this temperature. On the other side, if we use very high temperatures, we have a grain coarsening, which is can be especially dramatic in the case of the largest particles, as you can see in this graph. In fact, some of the grains can reach the size of the prior particles, as I have drawn here. And a final example, another superduplex stainless steel. This is the powder metallurgical equivalent grade of a very typical superduplex stainless steel. If we consolidate this powder with the typical heap parameters, we obtain a very homogeneous and fine microstructure with the ferrite within specifications, but with some sigma phase precipitating. This heap cycle has been transformed in a conventional heap press with a cooling rate, which is quite low. But if we perform this heap cycle in a more modern heap press equipped with an ultra rapid cooling device, in this case, it's possible to avoid the precipitation of the sigma phase, although in this case, it should be necessary to modify the heap parameters because, as you can see, the ferrite has increased. So this means that the cooling rate has also an effect on the final microstructure. So after describing the effect of the heap and process in the material, I will spend a few words on the components. Initially, I said that the change in volume is regular, it's homogeneous regardless of the direction, but in practical, this change in volume depends on many factors: the stiffness of the capsule. This means the material, the thickness, the quality of the weldings, their location. Also depends on the geometry of the powder cavity or the presence of density gradients due to deficient filling. If we take into account all these facts in the manufacturing of complex shaped components, large and of very expensive materials, then one can understand that having a tool that is able to predict these distortions and design the capsule in that way that it's possible to minimize machining operations is key. In this context, finite element modeling of heap using macroscopic laws is an effective method to predict densification. These models are more effective when they take into account the power-like creep and not only the plastic densification mechanisms. This is the example of our approach, Fade's approach, to predict the final shape. We're using elastic and viscoplastic model based on a WAPS model that describes the viscoplastic behavior of porous materials. Well, this is the equation we use to consider the contribution, the creep behavior of the capsule. This is the equation we use to, the constitutive equation of the porous materials. And this is a method that can be calibrated with experimental data. In our case, we perform tests, mechanical tests on fully dense materials, both the capsule and the material, the powder, already fully dense, and also some mechanical tests on porous materials. This method can combine mesoscopic analysis to consider the geometry of the pores, the arrangement of the particles, and also their particle size distribution. And just to finish, I can say that this model has also implemented a closed-loop iteration process that automatically modifies the initial dimensions of the capsule until the final dimensions of the densified alloy are within the tolerances. Here you can see a brief, an example of a turbine case of nickel superalloy, where by successive iterations, automatic iterations, we modify the shape of the capsule to compensate some distortions that are not desired to reproduce the final section of the capsule. Okay, you can see here with a higher detail this distortion we can counteract with this iteration. Final example, you can see here how accurate is this model. I don't know if you can distinguish the figures, but here we represent with these colors the difference between the final dimensions and the predicted dimensions, and differences are in all cases below 1 millimeter. So to finish, I could say that powder metallurgy, that heap consolidation of powders is a very flexible technology to process a very wide range of materials for many different applications, and with an improved performance compared to the conventional manufacturing process. Understanding the mechanisms that are involved in the densification of powders is a key aspect to obtain dense materials, but also with an adequate microstructure and hence properties. And finally, the current modeling developments can be a very powerful design to optimize capsule geometries automatically and obtain complex components, minimizing material consumption, machining operations, and of course, cost and delivery time. And well, this was all.
Thank you, Nerea, for this nice presentation. It was really comprehensive. I even learned a lot of things. You know, heaping is a very specific process that includes a lot of know-how. So thank you for explaining a lot of nice things to us. I think we have a question regarding your presentation. But Bruno, do you think we should pause in the questions now or wait until the Q&A session? I think my idea is that okay, for the audience, everyone can pose in the questions, or even after presentation of Jim, they can orally put on their pose their questions. So
we can make it at the end. Yes.
Yes, exactly. So for everyone listening, please at this moment just take your questions. Wait for your questions until we finalize the presentation of Jim. Okay, Jim, I see that you already started your presentation. So now it is rather applications and case studies for HIP. So the stage is yours, Jim.
Yeah, thank you. Thank you. I hope you can hear me.
Yes, we hear you. Bye.
Yeah, thank you, Neria, for a really in-depth view there of a lot of the powder-related HIP applications. And I'm going to try and give a brief overview now of the of some of the other areas that you can use HIP. And really, today there's a lot of focus on near-net shape parts, and of course there's a big buzz in the industry around additive manufacturing. We have the powder near-net shape parts that you just showed as well. And of course, we have castings, which are not powder related, but are very involved in the HIP industry. So I'm going to talk a little bit about each of these. The difference in these really is how the material is produced, and obviously, and the powder wire feedstock used for additive manufacturing obviously means that you're melting a powder or you're consolidating something in the solid state in the case of metal binder jet. For near-net shape parts, we have a powder that we're consolidating in the solid state, and in the case of castings, we're actually melting the material. So it's a solidification in a mold as the way of forming the part. There are four main areas basically that HIP is used today. You have consolidation of powder, you have the densification of products, you have diffusion bonding, or putting two different materials together. And the fourth one that you touched on at the end, then area is around high pressure heat treatment, and how you can use not only the temperature and the pressure in the HIP, but also the cooling rate and control the cooling rate to get a heat treatment in the same operation. So those are the four main application areas, if you like, of HIP today. If we look at consolidation of powder to start with, I mean, you talk now about the near-net shape process, and basically we have spherical powders today produced in inert environments. You either have gas atomized or plasma atomized powders today available, and many of these are actually using VIM or vacuum induction melted material as virgin material for the atomization process. So these are extremely clean powders. They have very nice grain sizes, of course, small grain sizes with no segregation. And you can see that the inclusion content is extremely low in these powders, which makes them very interesting for making parts out of. There are several powder batches that can be blended into one master heat for making very large parts. And of course, the particle size distribution can be managed through the atomization process, and also sieving or screening of powders later on. So this is I think powder metallurgy is a key cornerstone for many of the processes involving HIP. And these are made into these kind of parts. You can see to the left here a bend made for a 90-degree bend here for a nuclear application. You have some powder near-net shape parts there for the offshore industry as other examples. And these can be very, very large. You can see based on the palette there that the parts on the top there are standing on. You can see that these parts can be extremely large, and really they're only limited by the size of the HIPs available. And as you mentioned, the pressure is quite often around 1,000 bar, but today the standard units are up to 2,000 bar as standard for up to 1.6 meter diameter from us at least. Here's an example from a subsea hub, which is courtesy of Total. And on the left here, you can see the original cast parts with cracks in them. And this has caused many major problems, and also failures offshore, which are extremely expensive. And on the right, you can see the finished powder near-net shape hub, which was in duplex material in this case. So this is a great example of how powder can solve cracking issues, and also the very good quality of powder that's used in these processes gives a segregation-free, crack-free material. If we look at densification of products, these are used predominantly to improve the quality of castings or additively manufactured parts, and also sintered materials such as MIM is also quite common. And if we look at the casting as an example, I mean, you have the process itself is inherent to porosity. You can't really avoid shrinkage porosity and gas porosity being formed during the casting process itself. And of course, this leads to internal defects in the as-cast condition. These can be managed and planned, kind of where these are going to end up based on the solidification planning. And internal defects such as stress concentrations, crack initiation points, corrosion initiation points, etc., all have negative influence on the material. And of course, these give rise to NDT and weld repair issues. So I'll show you a little example of that now. I mean, here we have some mitigation of these problems, if you like, for castings today, where molds are basically have special channels involved, also in inherent cooling systems in the molds to try and minimize the porosity issues, and also move the porosity to parts away from the main body of the casting. So this is kind of the solidification zone is important. And 3D printed molds are extremely important today, and they're growing rapidly. So here, hot isostatic pressing is used for defect healing, reducing the weld repair basically in material. Also, it's giving properties that are extremely close to those of forgings. So quite often cast plus HIP material can be used as an alternative to forging. And of course, the complexity of the 3D printed molds means that we can also attain near net shape parts from another production method other than powder, which reduces overall costs as well compared with maybe machining out of blocks of steel. So these are some typical new trends, if you like, for hipping as well, where I think HIP in the castings industry is always been very strong. Powder has been a part of that, but the castings industry has actually been, the foundry industry has been predominant in the terms of the volume used in HIP equipment today. One of the reasons for using HIP for castings is basically to remove the porosity prior to machining. So you can see here on the left some examples of machine surfaces with dye penetrant testing on to just exposed pores that lead to corrosion issues, basically in offshore applications or petrochemical applications. So the flange sealing surfaces are a major issue. And quite often these can be on major castings, large castings. They can be ground out and weld repaired and then re-inspected. But this is a very expensive and costly process. It takes time, etc. So hipping first is a good solution, and also gives then properties very close to those of the forgings if you were to do it another way. Additional functionality can also be added to parts. On the left here, you can see a subsea template, also courtesy of Total, where you can see a couple of manifolds. I think I'll turn my laser on here. You can see here, there's a manifold here on the right, and also one hidden behind here on the left, actually producing hydrocarbons from the well, which often contain erosion products like sand, etc., which are produced from the well and go into the risers and up to the surface. And these sand particles, etc., rock particles, can cause enormous erosion problems in these kind of structures. So quite often diffusion bonded material is used to put some wear resistance in parts where you want to address this issue. Also, some thicker sections can be made, often with near net shape technology, to add some extra thickness just to counteract the problem and extend the service life. And of course, the design of the junctions can be adjusted especially for the near net shape technologies here to avoid this erosive behavior. And of course, the wear-resistant materials are an interesting area, which brings me to the kind of diffusion bonding area, which is also a major area for the use of HIP. And here we're joining together dissimilar materials in the solid state, so they're not melted. So it's solid to solid, powder to solid, or powder to powder, depending on the application. And different materials can be combined. So here's some examples. You can see diffusion bonding of wear materials with like cobalt-based alloys or tool steels, metal matrix composites, etc. Typical stellite kind of material. And on the top here, you can see a forging with a welded-on stellite 6, and in the bottom here, you can see a HIP instead. And these are quite common application areas for hipping today, using powder in many cases. And HIP of selected areas gives a wear resistance, which can be controlled by the thickness of the powder, and it can be used on a substrate material, which can be the pressure-bearing part, if you like. So compound solutions involving different materials are quite common today to solve problems for end users. Here's an example of a valve seat. You can see where there are actually 4 materials in this valve, and this combination of different powders in different parts, and this is a powder near-net shape construction. So powders are filled into the can in different areas where different properties are needed, including intermediate layers in between materials that maybe can't diffusion bond together easily. So here the very robust designs can be made with different powders, and of course a lot of know-how in how to do this. But this is also a very interesting application for HIP. Lightweight structures are also being used, of course, when adding topology optimized parts, if you like. There are different ways to do this today, and casting is one, 3D printing is one. We have also the near-net shape area, of course, where improved material properties can be achieved using HIP. With narrower tolerances, stronger material, etc. And you can also place material with different properties where you want to put it, and avoid welds, which is extremely interesting from an NDT or non-destructive testing perspective. And this can give very, very strong, reliable structures for the industry, all kinds of different applications. And by combining the different techniques, HIP can really solve issues for customers. High pressure heat treatments, the last one of the 4 here, where basically combining heat treatment into the HIP cycle is a real trend for some of the industries today. And here's an example for a nickel-based single crystal, where combined heat treatment and aging cycle has been done inside the HIP. So here you can actually quench material very quickly, or control cool at say 200 C per minute if you want. And you can actually control cool these, add an aging step, and combine several processes into one process. And this is an example from the University of Bochum, where they've done a lot of work on this ERB01 alloy. So there's a lot of literature to read on this. And this can be very interesting in terms of the microstructure, where the conventional method may be involving several steps. The heat treatment can lead to some porosity reopening, whereas doing this under pressure, we can actually stop this happening and also get a very, very fine microstructure from doing this. So the cooling capability of HIPs today is an increasingly important part of the industry, where we're not only talking about hipping and separate heat treatment today, but also combined cycles to improve improved properties for specific applications. And of course, this is possible for many different alloys based on the cooling rates available. So you mentioned duplex earlier, Neria, and duplex, super duplex, also hyper duplex is fully possible in this cooling regime. And of course, it's very, very important now for titanium aluminide as an example. Cobalt chrome is also extremely important. And we see the use of very high pressures here up to 200 MPa with high-speed cooling being important for areas such as high nickel alloys such as C22, C276, etc. So these areas are extremely interesting for the industry, and I think there's a lot of work and R&D going on in this area. So those are the 4 areas. It's the last slide in my presentation, and I guess we can. I'll close this down, and we can move to questions.
Okay, thank you, Jim. This was a really nice presentation. Yes, we have a quite good number of questions in the chat. Maybe I can start one by one. So the first one is from Onur. So Onur, if you're online, you can unmute yourself and pose your question. So Onur, do you hear us?
Yes, Mr. Boss. Yeah.
Hi, Onur. So I think you're asking about the gas. Please go on with your question.
Yeah, actually, maybe I can ask it to the Jim, or both Jim and the doctor. So the used gas should be always the high purity argon, or can we use less purity argon or other kinds of gas? So I want to just ask the projects before, if someone worked on it. Thank you.
I mean, it depends very much on your application, I would say. I mean, Neria, feel free to fill in here. But if it's a near net shape application, usually the canister is made of a carbon steel. So maybe the quality of the argon's not so important because you have a carbon steel can, which will be later pickled away. But if you're looking at a cast part or a additively manufactured part, of course the purity of the argon is important, and that's important to have a high purity. But having said that, we can also use different gases in the HIP. So nitrogen is used a lot for ceramics, as an example. There are sometimes some active gases added as well for specific effects, like nitriding can be done in the HIP, carburization, etc. So some active gases can also be added into mixtures sometimes, depending on the application. So yeah, it's a long answer to your question, but usually for near net shape, it doesn't matter so much. For the others, usually pure gases as much as possible, and sometimes some additions of active gases.
Well, thank you.
Yeah.
Thank you, Jim. Yeah.
Suppose if I can, I have one more.
Yeah, if it is short, why not?
Yeah,
we have some other questions in line.
Okay, so when we work with the ceramics, we faced sometimes about the carbon contamination. So because we had the graphite heating materials, so is it common, or do you have any idea on that? Thank you.
I think I can try to answer. I don't have much experience in ceramics, but I think it's a quite common problem unless you working, at least even with working with argon, unless you provide a protective layer that avoids this diffusion of carbon, is something that can be quite common. But it's possible to isolate your sample and protect it from this activity of carbon.
Yeah. And graphite furnaces are used at these very high temperatures usually, and it's isolating it with the use of other ceramics usually to protect the parts, which is the key.
Thank you.
Okay.
Okay, our next question is from Kadir. Kadir, if you're online, you can put on your question yourself.
Yes, hello.
Hi.
My name is Kadir and I'm speaking from Budapest. So I have a very simple question that how can we say that HIP is better than other sintering techniques, gas pressure sintering or hot pressing? Give me the specific. You mentioned generally that these are the advantages are better, but could you please explain a bit? And I have another question that we use the gas. It can be inert gas, and it does not produce any porosity in it during using the gas. And I don't know, I didn't understand maybe this mechanism. And thank you very much.
Okay, I think I can try to answer your first question. Consolidation of powders by heat is not necessarily a technology that competes against sintering, gas pressurized sintering, or hot pressed. Heap is more suitable to produce near-net shape components, large components, and components that otherwise need long delivery times by machining, as you have seen. If we want to obtain, for example, all these components of the automotive industry that are pressed and sintered, in that case, obviously it has no sense to use the heat press. The cost could be unaffordable because we would need very tiny capsules, and the encapsulating would be unaffordable. In the case of hot press, we have some experiences that heat press can be a good alternative to hot press in some applications. For example, in cutting tools with diamond. In those cases, it's possible to achieve higher densities. And in that case, the mechanical properties are higher, but something that maybe I didn't mention in the presentation, the reliability is higher. So you can ensure zero defects, and well, this dispersion in the mechanical properties is reduced. So the message is that HIP is not a technology that is competing against other sintering technologies. They are different. They have different business niche.
Yeah, I mean, maybe I can add on to that, Neria, as well, because if you look at the common sintering technologies for MIM, for metal binder jet, etc., these kind of, I mean, they get to a certain point where you have to go to very high temperatures to get the sintering complete. So there are processes today where sintering is stopped at, say, 94% when you have a surface tight surface, if you like, that the argon doesn't penetrate, and then you can use HIP to fully densify the material and get very good fatigue properties. So basically, fatigue is the challenge, I would say, with MIM and other sintering technologies. They can't reach the fatigue levels needed for many of the applications. So if you look at binder jetting as an example today, one of the challenges is to get all the way up to the fully dense material compared with laser and with maybe a better density. So here HIP is used, and HIP is used for improving the fatigue resistance for the parts, and for MIM, it's very common for repetitive fatigue parts, if you like, in small in aircrafts, as an example, for MIM parts. There's a lot of those in the aircraft industry, and they HIPed. So they complement each other, I would say, the sintering and the HIP. HIP is almost always used when it's a fatigue-related issue in the application.
Thank you, Jim.
I think his second question was regarding contamination. I think contamination or diffusion of gas.
Diffusion of gas, yeah.
Yeah, of the pressurizing media. Yeah, it's something that can happen. In some cases, it's possible to see an increase of for example, the argon content after heaping. In those cases, it's generally produced due to defective welding. some cases welds are tight at room temperature, but at high temperature, well, they can evolve in a way we wouldn't like, and some very tiny leaks can develop. These leaks are enough small enough to allow densification, but maybe they can fail at the end stage of the heap, and a small diffusion of argon can take place. When I talk about small, I mean maybe 5-20 ppm of argon, and this is enough to cause a brittle fracture of certain components. So it's something very critical in neon shape heap.
Yeah, I think in your first slide, one of your first slides there, you showed if there's a surface connecting defect from a solid part, basically the hip can't close it, and it's the same if you have a leaking capsule for the near net shape. Basically the argon gets inside, and it can be an issue. And that's why such it's a very, very long process actually to do a lot of NDT on the welds to ensure that the capsules don't leak before hipping. But if you look at solid parts like castings or additive manufactured parts, MIM, etc., then the surfaces are, if you have a density above 95%, which is, I guess, compared with powder metallurgy, near net shape is like 70%. Here, 95 and above, the surface is usually tight enough to stop any gas getting in. And this is usually there's no surface connecting porosity at that time, so the gas can be used to close it with the hip.
Okay, Jim, thank you. We are getting out of time step by step, so I want to move on further quickly. So we have the next question from Sushil Kumar. If he's online, I can put it. We can ask him to ask his question, or I can read it directly. He asks on any examples of advanced ceramics, especially for transparent ones. Is it possible in hipping?
Yes, hip is used for translucent ceramics, yes.
Okay. So the next question is from Nawaitos. He asks if there is any material thickness limitation for hip. That was one of my questions also.
How big is your hip?
Yeah, it's you can see huge billets or bars produced by hip. Certain types of steels that cannot be produced by casting, and they are decant after consolidation and rolled, and these billets are as thick as 1 millimeter in thickness. I think the limit in general, the limit is imposed by the hip press. Maybe in certain applications, the post-hip heat treatments that is necessary to apply, for example, to dissolve some phases or even to precipitate them, can limit this thickness because the cooling rate, for example, if we need to quench a component to avoid, for example, in oil and gas super duplex steels, we need to perform quenching after the solution annealing, and we need to ensure that the cooling rate in the point of the component that is farthest from the surface, this cooling rate is above the minimum cooling rate to avoid this sigma phase. So it depends on the application and on the material.
I fully agree. Yeah.
Okay, thank you. Now the next question is from Dov. Dov, if you are able, you can put on your question, or I can read it. Okay, let me read the question. How do you plan to close porosity in the inner side of the part and the outer side, part side, when it is closed porosity?
Okay.
So could you understand it?
Yeah, it's all to do with the isostatic pressure.
Yeah.
So basically, if there's a channel inside a part, the gas will go inside, and the pressure inside there is the same as the pressure on the outside of the part.
Yeah.
So it pushes from both sides top and bottom. That's why it's called isostatic pressure, because it's coming from all sides. If there's no channel into the part, then there's only pressure from the outside, and that will close the porosity inside the part anyway. The material moves as Nerea explained earlier.
Okay, thank you. So the next question is from Tom Sellers. Tom, if you are able to quickly unmute yourself, you can ask your question directly.
Hello, thank you for letting me ask the question. I was just intrigued because I work for Liberty Powder Metals. We'll be supplying powder into the PM HIP market, and one of the things that we are looking at is trying to obviously offer a good service to all our customers. And so to understand this, we'll need to know what we're specifying to the HIP operators. And I just wondered, for canisters, for alloys like nickel alloys and potentially even titanium, what the suitable vacuum level is inside the canisters to avoid any oxides or any other types of defects. I've read that less than 1 torr from a number of different sources, but I just wonder if someone could clarify that for me.
I'm not sure whether I follow your question. You're talking about, we're wondering about the vacuum level.
Inside the HIP
Yeah.
canister, if it's got powder inside, so you have to evacuate it and outgas it. And I just wondered what the
I would say that there are different techniques for degassing, and different companies have their own IP around this. So sometimes the canisters are heated, sometimes they're not. They have different purging regimes, different vacuum regimes. So I think there's a bit of IP around that. So you'll have to ask your customers.
Okay, fair enough.
Yeah, and it's not only vacuum, but it's also degassing. You can have a very good vacuum at certain conditions. Yep. But if, for example, you heat your capsule or your powder, you activate some release of absorbed gases. So you lose the vacuum. So it's not only a question of quality of vacuum. It's not static vacuum. It's something more related to removal or any species that can be absorbed.
Yeah, I understood that the capsule would be heated at some point in some processes to ensure that they've outgassed it. But I just wondered what the ultimate pressure needed to be to sort of ensure that you didn't get any oxides forming or nitrides depending on the alloy. That was all.
It's about purging, I would say. It's a combination of purging and vacuum and heating. But you ask your customers.
Okay, great stuff. Thank you very much.
Thank you.
You're welcome. So the next question is from Ilaria Forno. Ilaria, if you are able to unmute quickly. Yeah, you're here. Yep. Okay, go on with your question.
Yeah, hello. I'm working in the jewelry industry, so we are using a lot of casting, investment casting, and since the quality now, the level of required quality is increasing, I was wondering if it's possible to apply HIP, and if in that case it's needed a specific shape container, or if the process can work with different parts all together. So I'm a bit far from this kind of processes, so I would like to have a bit more information if it's possible.
Yeah,
Thanks.
we have. I mean, there are lots of applications in the jewelry industry today. I mean, you have investment casting, of course, of gold, platinum, and all the other special metals. It's hipped before polishing to remove porosity so that you get a nice glance. So many of the high-end guys are already hipping. And if you look at the AM industry, it's also moving into gold as well as and so here you can see printed parts where you have special designs, and it's the same thing there really, where you're acting using HIP to close the porosity and then doing your surface treatments to get the nice glance on the parts. So the jewelry industry is already using this big time, and as is the watch industry for MIM parts. It's the same basic idea here with removing porosity to get the surface finish nice afterwards. And we have a lot of knowledge around this area. So
Perfect. Really interesting. Thank you very much.
Thank you.
Okay, so our final question comes from my colleague Bruno Vicenzi. Bruno, if you want to ask yourself directly.
Yeah, I have a couple actually. First was what is the sensitivity of shrinkage to powder segregation during the filling? And the second is completely different. I was wondering if it's possible to include solid inserts while compacting the powders, maybe from different materials, so that you can have a composite final part, if there are any examples.
Do you want to take it, Miria? Or
yeah, I can start and then you you continue. Okay, powder segregation it can be a problem. In fact, if you remember in one of the last slides I showed some defects, some defective filling, lower density, or even powder segregation because of excessive tapping or vibration of the capsule with not the proper conditions, can make then some powder particles go to the bottom and other go to the upper part of the HIP capsule. And the densification mechanisms of rates, of densification rates of particles of different particle size are different. So some parts can shrinkage in a different way than another as a consequence of this segregation and also as a defective filling. And it's something that some models are taking into account, modeling this segregation. There are a number of research activities on this field, and it's something that can be considered.
Yeah. And the major producers of near-net shaped parts today, there's a lot of IP around how they fill their cans. And so I think that's an area we obviously can't talk about, but it's that how you fill your can and how you place the different powders, mix the different powders is key to getting the right result if you want to be able to predict it. And as I showed in the example earlier with the valve stem, you can you know, if you want to have those powders stay in place, you have to fill them in a certain way. And how you do that, I mean, that's up to the guys doing it. But I mean, we're basically just putting pressure and heat on afterwards. So it's a different. It's not really our IP, but the IP on how to fill the cans is with those companies.
And regarding the hipping, combining powder and solid parts, yeah, it's possible. It's something that it's done. Yeah. For example, for cladding, for nuclear application, it's something that it's commonly done. Yeah.
Yeah. And I think it's just quite common actually to mix powder and solid parts. It's done in the industry. And I see one more question here also on can we close microcracking with hipping? And the answer is yes, of course. I just saw one more here from Dove. So closing microcracks is also what HIP is about. As long as you don't have the surface connecting porosity, you're fine.
Okay, thank you. I think I covered all the questions, but still, if there are any questions, so we have our last minute. We can go on with the last question. Are there any questions? Okay, then I will pose the last question myself. So I see in the presentations that if the pressure, there is the pressure, the temperature and the time. So we have a certain relation in between them. So is the relation always the same with different type of materials, or for different type of materials there are different relations between these temperatures, pressure and time? That is this something kind of know-how for each material, or is it something that very easy to determine with some formulas? That's my question.
Well, I didn't thought about that. I'm not sure whether it is a straightforward relation. From our experience, well, we know it's possible in that example I included, it's possible to reduce the pressure by increasing the time, but it's true that some materials are more sensitive to the increase in the temperature than others. Mm-hmm. It's something that, well, I think it depends on the material on the family of this material, and also of the alloying elements it contains.
Yeah, and if I add on to that, I mean, if you think about a normal TTT diagram with changes in the material, we have obviously temperature and time usually in these. If you add pressure, then you have a kind of a three-dimensional graph to think about. And then if you add the cooling rate onto this, then you end up with a very interesting situation. Mm-hmm. And you also have to think about how, the phase transformations, what's happening in the material at different temperatures and pressures also. Yeah. So the kinetics of the material as well. So it's a very complex area, and there's a lot of research needed in this area. It's not so much been done yet. There's been some work in some alloys, but it's a very interesting area. But to start with, I would say we're basing most of the HIP cycles today on the casting industry. That's where the service providers offering HIP services today are basically offering around the casting cycles to get a complete cycle to fill. But there are, of course, also there's a lot of work going on in special HIP cycles where maybe the relationship between pressure, temperature, and time can be played with a little bit, and also cooling rate, of course. So depending on the application and the end user and what's being, if you have access to a HIP or not, then things can change. So it's a very exciting area.
Thank you very much. So it looks like we will have much more projects on this topic, huh?
We hope so.
Okay, so thank you, everyone. This is the end of our webinar. It was really nice and comprehensive. So firstly, I would like to thank our speakers, and then thank you all for joining our webinar. I think the next one will be on functional materials. You can follow all the latest news about EPMA and its activities through our website and through LinkedIn. So thank you very much for everything, and goodbye.
Thank you very much. Bye-bye.